Chemistry can feel like this secret language, right? It's all these complex codes and symbols, but what if I told you it's not so secret, that it actually has an alphabet and a grammar, just like any language you already speak? Well, today, we are going to crack that code, and I promise, by the end of this, you'll be able to read it.
I mean, look at this. You probably know H2O is water. That one's easy. But C2CL4 F2? Wow, that looks intimidating, doesn't it? But here's the thing. It's not just a random jumble of letters and numbers. It's a name. It has rules, it has structure, just like a real language. Honestly, the only difference between being able to read the first one and the second one is just knowing the alphabet and the grammar. That's it.
So, here's our game plan for getting fluent. First up, we're going to learn the alphabet, how to decode those chemical formulas. Then, we'll dive into the grammar, the rules for combining everything. After that, we'll tackle the chemist's big secret for counting atoms you can't even see. And finally, we'll put it all together, play detective a bit, and really see why this language is so incredibly powerful.
All right, first things first, let's learn the alphabet of chemistry. At the very heart of this language, it's all built on these things called ions. Basically, they're just atoms that have picked up a positive or a negative electrical charge.
Okay, so this alphabet has two main types of letters. First, you've got cations. Those are the positive ions. And honestly, these are the easy ones. They just keep the name of their original atom. So a sodium atom, which is Na, just becomes a sodium ion. Simple. But then you have anions, the negative ions. They're a little different. You take the root of the element's name and you tack on "ide" at the end. So chlorine, or Cl, becomes a chloride ion. Sodium ion, chloride ion. See, not so bad, right?
Okay, so we've got our letters down, the ions. Now let's get into the grammar. These are basically the rules for how we combine those letters to form chemical words, which, we call compounds.
So there are really two main grammar rules you gotta know. The first is for ionic compounds. That's when you have a metal and a nonmetal coming together. For these, you literally just smash the two ion names together. So Na plus and Cl minus becomes sodium chloride. Super easy. But for molecular compounds, that's when you have two nonmetals, things get a little different. We actually have to count the atoms. And to do that, we're gonna need some prefixes.
And this right here is our counting system for those molecular compounds. These are just Greek prefixes, and they tell us exactly how many of each atom is in the molecule. So di means 2, tri means 3, tetra means 4, you get the idea. And this precision is absolutely crucial. It's what makes the difference between, say, carbon monoxide, which is a toxic gas, and carbon dioxide, which is just the gas we all breathe out.
All right, time for a little pop quiz. Let's put this to the test. I've got 3 formulas here. Based on that prefix rule we just talked about, maybe pause for a second and see if you can name them yourself. Go on, give it a shot. No one's watching.
So, how'd you do? Let's check your work. N2O. Well, it has 2 nitrogens and 1 oxygen, so that makes it dinitrogen monoxide. Next, CbR4 is 1 carbon and 4 bromines, carbon tetrabromide. And last one, SF6, is 1 sulfur and 6 fluorines, sulfur hexafluoride. Look at that. You are literally reading chemistry right now.
Of course, just like any language, there are always some special cases, right? Acids are a great example. They get a totally new name when you dissolve them in water. So the gas hydrogen chloride suddenly becomes hydrochloric acid. Think of it like a regional dialect. But knowing what something is called is really only half the battle. The next big question is, how much of it do we have?
Okay, so we've got the naming part down. But how in the world do you count things that are so small you can't even see them? This brings us to, and I am not exaggerating, one of the most important ideas in all of chemistry, the mole.
And no, don't let the name fool you. We are not talking about the little furry animal that digs up your garden. In chemistry, a mole is just a unit for counting. It's a lot like how we use the word dozen to mean 12 of something. A mole just refers to a specific number of atoms or molecules. The only real difference is that this particular number is, well, it's unimaginably huge. And this is that number. It has a name. It's called Avogadro's number. It's 602 sextillion. That is a mind-boggling number. That's how many particles are in just one single mole. So why is it so ridiculously huge? Well, because atoms are so incredibly tiny. You need a massive pile of them just to get an amount that you can actually see and, work with in a lab. So, the obvious question is, how do you count out 602 sextillion atoms? And the short answer is, you don't. You can't. Instead, you do something much smarter. You count them by weighing them. Just think about it for a second. If you know how much a single penny weighs, you can figure out how many pennies are in a giant jar just by throwing the whole thing on a scale, right? Well, chemists do the exact same thing, but with atoms.
And what this gives us is a super clear two-step pathway. If you know the mass of your substance in grams, you can use what's called its molar mass, which is just the weight of 1 mole of that stuff, to figure out how many moles you have. And once you have moles, you just multiply by Avogadro's number, and bam, you know the exact number of atoms. This is it. This is the critical link between the visible world we can weigh in grams and the invisible world of atoms.
Okay, let's switch gears a bit. It's time to put everything we've learned together and become chemical detectives. So how do scientists actually figure out what an unknown substance is? Well, they gather evidence and they use it to figure out its formula.
So the very first clue a chemist usually finds is something called the empirical formula. Now this is just the simplest whole number ratio of atoms in the compound. It's not the whole story, not by a long shot. The true, complete identity is the molecular formula. So for example, a compound's simplest ratio might be CH2, but its real formula could be C2H4.
So how do they find that crucial first clue, the empirical formula? Well, it's a really systematic 5-step process. They start with the percentage of each element in the mystery compound. They pretend they have 100 grams, so the percentages just become grams. Then, they use that molar mass we talked about to convert those grams into moles. That gives them a ratio of atoms, which they then just simplify down to the smallest possible whole numbers. This is the exact procedure chemists use to figure out a molecule's basic blueprint.
But wait, where does that initial evidence even come from? I mean, how do they get those percentages? A really common method is called combustion analysis. Scientists will literally, very carefully, burn a sample of the substance. They then precisely measure how much carbon dioxide and water it produces. And from that data, they can work backward to figure out exactly how much carbon, hydrogen, and even oxygen was in their original, unknown stuff. It's pretty cool.
So, let's recap. We've gone over the alphabet, the grammar, and even some of the detective work. But why? Why does this language of chemistry actually matter? What's the big deal?
Well, what we've really learned today is that chemistry isn't just some random, arbitrary set of rules. It's a logical language. And that concept of the mole, it's probably the most important word in that entire language. It's the bridge that connects the invisible world of atoms to the visible world we can actually measure and manipulate. And mastering this language, that's what allows scientists to do everything from discovering new materials, to developing life-saving medicines, to engineering all the amazing technology that's all around us.
I mean, just think about it. Everything around you, literally everything. The air you're breathing, the food you eat, the phone that's probably in your hand right now, it's all made of these molecules. And every single one has a specific name and a specific formula. You now have the key. You have the tools to start decoding that world. So the only question left is, what story are you going to choose to read first?